Hello everyone. So today what we are going to talk about is the topic in the quantum mechanics, that is linear harmonic oscillator, that we refer to as one-dimensional harmonic oscillator. So we will study about its Hamiltonian, raising and lowering operator, and many other small topics. So let's start. So what is an harmonic oscillator? In classical mechanics, you study for a harmonic oscillator, the potential vary as a function of x squared. That is, potential is equal to half k x square. You study that. Okay. So if there is a classical particle, then this classical particle is bound to oscillate within some regime that we call as classical regime. So we refer that it is in a bound state. In quantum mechanics too, if there is an oscillator which have potential as v is equal to half kx square, then it also have a bound state. So we are going to discuss all about that. So let's start. So here potential is equal to half kx square. We can replace this k by m omega square x square. So now the Hamiltonian, what's Hamiltonian here is? Hamiltonian is nothing but the total energy of the system. Hamiltonian H is equal to kinetic energy P squared over 2m plus potential energy V. So it comes out to be P squared over 2m plus half m omega squared x squared. So now let's find out its solution using Schrodinger's equation. So what does it say? Schrodinger equation. I am here using time independent Schrodinger equation, and that too only in one dimension. So H Hamiltonian operates on psi gives energy eigenvalue E psi. So we can write it as minus h bar square over 2m d2 over dx square plus potential energy term half m omega squared x squared. This all operating over psi, giving E psi. So let's move forward. So we can write it as d2 psi over dx squared plus 2m over h bar squared multiplied with E minus half m omega squared x squared operating over psi is equal to 0. Remember, here k, that is propagation constant we call it. Here k will not be a constant, as k is given by square root of 2m E minus v over h bar, as E minus b here depends on x. So this k here is not constant for a harmonic oscillator. So let's move forward again. Okay, that's this k and the k we mentioned above as half kx square are totally different things. Let's move forward. As Hamiltonian H is equal to p squared over 2m plus half m omega square x square, we can write it as Hamiltonian over h bar omega is equal to half m omega over h bar x squared plus 1 upon 2m h bar omega p squared. Rearranging, Hamiltonian over h bar omega is equal to square root of m omega over 2h bar squared x squared plus 1 upon square root of 2m h bar omega squared p squared. So now I am here defining two operators. What are these operators? These operators are, one is A is equal to square root of m omega over 2h bar x plus iota p over square root of 2m h bar omega, and other is A dagger. A dagger is defined by A itself. We just replace iota by minus iota. So we will get m omega over 2 h bar x cap minus iota p over square root of 2m omega h bar. Later we will find out that we will conclude that this will be known as lowering operator and this one will be known as raising operator. We will see why they are called lowering and raising operator later. So moving further, you must have understood this thing that above a bar and a dagger are Hermitian conjugates to each other. Okay, so that's not the thing that I need to discuss actually. Now we will move on to find out a dagger a. This is very interesting. We will find out and then we will infer something from this. We will get m omega over 2h bar. How will we do that? We just multiply this a dagger with a. This will come out to be m omega over 2h bar x plus iota 1 upon 2h bar x p minus iota 1 over 2h bar p x plus 1 upon 2h bar m omega p. What I have done, I have just multiplied these two operators. This will be equal to m omega over 2h bar x squared plus 1 upon, I am writing this term first, 2h bar m omega p squared, and then these two terms combinedly I can write as plus iota over 2h bar commutator of x and p. Okay, so further moving, a dagger a is equal to, you notice if I take common 1 upon each bar omega from first two terms, what will I get? P square over 2m plus half m omega x squared, and this term, what we know, commutator of x and p gives us iota each bar. So h bar cancel out with h bar, and further I can write this as Hamiltonian of the system. So this become Hamiltonian over h bar omega minus 1 over 2. Iota square is minus 1. So a dagger a, I got h bar over h bar omega, Hamiltonian over h bar omega minus half. Similarly, if I do a into a dagger, I will get h Hamiltonian over h bar omega plus half. Okay, so from both I can always write Hamiltonian as a dagger a plus half h bar omega, and this will be equal to, from here, a into a dagger minus half h bar omega. So this is a result you may remember. That's not compulsory at all. So let's move further forward. Now I am trying to find out one more relation. What that relation is? Relation is h bar commutator with a dagger a. So one having an insight can directly answer that. The answer will come out to be 0. Why? We know that if two commutators are functions of, if the commutating things are functions of each other, then the commutator comes out to be 0. So let's actually prove it. So I can write Hamiltonian as a dagger a plus half h bar omega comma a dagger a. So I can write it as a dagger a h bar omega a dagger a plus half h bar omega commute with a dagger a. Now in this commutator, half h bar omega is a constant, so the commutator will come out to be 0. Now this, in this commutator, this is function of a dagger a, and this is also function of a dagger a, so commutator will again come out to be 0. So finally answer is 0. So the Hamiltonian commutes with a dagger a. Similarly, the Hamiltonian will also commute with a dagger. Okay, so moving further, now I am trying to find out commutator of a and a dagger. You just think of these some small problems. So if I want to find out this, how I can do this? I will simply write a dagger minus a dagger a. Now I have done this before, that a dagger a A dagger is equal to h bar Hamiltonian over h bar omega plus half, and what is my ये half dagger A, it is Hamiltonian over h bar omega minus half. So this and this will cancel out and we will get what? 1. So similarly, if one find out A dagger and A commutator, it will be minus of A comma A dagger commutator. So it will come out to be minus 1. So moving further, if one wants to find out A dagger A comma A, this commutator, how will we do this? So we can write this as taking A dagger outside, we can write first it like this and then plus we can write it as this will become A outside and then A dagger A. This is the property of commutators, you know, I think. So this will come out to be 0, same things are commutating, and this we have already found out, this is minus 1 from here. So this will come out to be minus of A. Okay. So these are some basic mathematical expressions you may think of that we have concluded here. Now we will move again further forward. Now we have from above discussion that commutator of Hamiltonian with A dagger A comes out to be 0. Okay. Since they both commutate, so they must share the common eigenvalue. So let there is state n be the eigen state, this is state n be the eigen state corresponding to the eigenvalue n for operator A dagger A. So how can I conclude that A dagger A is a will have this eigen state? Okay, so this is an eigen function. How can I conclude that? As it commutes with Hamiltonian, so they must share some common eigenvalues, and if they are sharing some common eigenvalue, so this must also be. So if this n is an eigen state of A dagger A, then it must also be eigen state of h bar. First of all, I will write A dagger A is equal A dagger A operating on n is equal to n where n is the eigenvalue. This cat n is the state and A dagger A is the operator. Okay, so now I will write as Hamiltonian operating on cat n is equal to A dagger A plus half h bar omega operating on cat n. So how can I write it? I can write it as this will what will it come out to be? I can write it as h bar omega A dagger A operating on n plus this half h bar omega. Okay, so h bar omega is already outside, half operating over n. Okay, so how can I write it? If A dagger A operates on n, it gives me nothing but n cat n. So I can write it as h bar omega n cat n plus half cat n. So it will give me n plus half h bar omega cat n. So what we conclude, if Hamiltonian operates on this state n, we get n plus half h bar omega. So what is this? This is the eigenvalue corresponding to the Hamiltonian operator. So what we call this? This is energy eigenvalue. So I can write as En, where n is the state, is equal to n plus half h bar omega, where n can go from 0, 1, 2, 3 and so on. So what will be ground state energy, we say? The ground state energy is the minimum possible energy. So it will be the energy corresponding to n is equal to 0. So what will be that? It is equal to half h bar omega. This is not 0. If this oscillator had been a classical oscillator, then the minimum energy the oscillator can have is 0. Okay, but in case of a quantum oscillator, a quantum harmonic oscillator, the 0 point energy is not actually 0, it is half h bar omega. So, in today's lecture, we will restrict our linear harmonic oscillator discussion to this point. In the further coming lectures, we will study more about these lowering and raising operators. What does they really mean? So, I'm just giving you some clue. This raising and lowering operator are actually based on energies. If I am using a lowering operator, then the energy will correspond to the energy just lower stage, to the just lower states. Suppose that we say n minus 1 state, and if I am using raising operator, then the energy will come out to be the state just above it. So, okay, let's conclude this lecture here. We will meet in the next lecture. Thank you.